Now that we see how to generate constraints, we should ask ourselves, how do we add the constraints to our formulation? Specifically, there's going to be a problem. In the procedure we just saw, we can potentially generate quite a few constraints. In particular, we can have an exponential number of constraints, say 2 to the n. We can't add all of these constraints to our formulation. If we did, then solving the resulting linear program would be useless. It would just take too long. In general, this was a problem whenever we looked at the convex hull of X. It can potentially contain a lot of constraints. We don't want to add all of the constraints, though. What if we were able to add just the constraints near the optimal solution? This is a good idea because what we'd like is just to get a good relaxation near the optimal solution. We don't care about any of the other feasible points. If we can somehow add constraints near the optimal solution iteratively, we would have an algorithm that would do good things for us. We're going to discuss precisely that. We're going to discuss a procedure that's going to add constraints near the optimal solution in an iterative fashion. An alternative motivation for this procedure we're about to introduce comes from branch and bound. Recall that in the branch and bound algorithm, at a particular node, we're going to compute the bound, we're going to branch, or split our feasible region, we're going to compute bounds, and then we're going to eventually prune nodes. This is the branch and bound algorithm. The branch and bound algorithm can get into a particular case where adding constraints can help. To see where constraints can help, we're going to consider having a problem P, our main problem, and then branching to create the subproblem P1. There's other subproblems created by this branch also, but we didn't show them in the tree. We branch on P1 to create the subproblem P11. We again don't show the other potential children by this branching process. At each one of these nodes, we're going to compute an upper bound. We're going to consider P as a maximization problem. So the upper bound we can compute can come from a relaxation, for example. The bad case that we're interested in is when the upper bound of the parent node is equal to the upper bound of all the children node. This is particularly bad because in some sense it says that we've made no progress. We can see that this is actually a pretty common case when we're looking at relaxations. For example, we can have a problem P, and we're going to compute the upper bound by taking an LP relaxation. The LP relaxation solution is denoted by XLP. And we can suppose that the first entry is 0, the second entry is 1, and the other entries are both 1/2. In our branching process, we can split by taking a particular integer and fixing it. In this case, P1 is defined by taking x1 and setting it equal to 0. It's obvious that if we did this, that the linear programming solution wouldn't change. We would have the same LP solution. If we split again by fixing the variable x2, say setting x2 equal to 1, the LP solution again doesn't change. In this case, the upper bound we compute is the same for all these different subproblems, and we don't make any progress on improving our upper bound. This is a bad case. So now we can consider what to do about this particular bad case. Let's suppose that we're solving the relaxation and we come to a solution, x, like the one we've seen in our example, that's infeasible. Rather than just ignore the fact that this is an infeasible solution, instead we can introduce some constraint that's going to cut off x. That is, we're going to introduce a constraint so that x is no longer feasible. We're going to add this constraint to our relaxation and then solve the LP again. Here we have a visualization of exactly what's going to happen. Here, our feasible region is denoted by the points in X. Our polyhedron, our original formulation, the one that the linear program is going to maximize over, is in this future color, and we call it P. Finally, we have a new constraint, denoted in green. When we solve the linear program solution, our optimal solution turns out to be X. And although this is feasible for the polyhedron P, it's not feasible for x because it's not an integer point. So we introduce a cutting plane or a constraint that's going to cut off x. The constraint in green is going to prevent x from being a feasible solution anymore. It's no longer in the feasible region after we've added this constraint. In this way, by adding this constraint, we're somehow improving our branch and bound technique. We're not going to do any redundant work of computing upper bounds in subproblems. The technique that we're describing is called the cutting plane algorithm. The constraint we've added is called the cutting plane. It's called a cutting plane because it cuts off a previous solution that has been found to be infeasible. We can think about this cutting plane algorithm in three distinct ways. The first way is the way that we've introduced it. The cutting plane algorithm is some enhancement to the branch and bound algorithm. Whenever we branch and we find an infeasible solution, we add an additional constraint that's going to get rid of this infeasible solution. Then we can branch and include this new constraint in every further subproblem we solve. The second way we can view the cutting plane algorithm is with respect to our original motivation. We wanted to introduce constraints, but we know we can't introduce all of them. We can only introduce a subset. So we'd like to introduce the constraints that are near the optimal solution. The cutting plane algorithm does exactly that. We can see that the point x that our linear program found is close to the true optimal solution. And we've introduced a constraint that's close to the true optimal solution. For example, the constraints we're adding aren't going to be on the other side of our polyhedron. So the cutting plane algorithm is a method to add constraints to our formulation where the constraints are close to the optimal solution. The third way we can view the cutting plane algorithm is as an independent algorithm in its own right. What we can do is we can solve a linear program relaxation and continuously add constraints to it until we end up with an x that's actually feasible. Once we find an x that's feasible, we don't need to add any more cutting planes. So the cutting plane algorithm can be an independent entity on itself, continuously add constraints until we find a feasible solution to the problem that we'd like.